Hello everyone, I am Tianxing Chu, and I am honored to present our latest work, Texture GS. Disentangle the geometry and texture for 3D Gaussian splatting editing. In recent years, many previous works has fully explored how to edit NeurF-based 3D scenes. However, all of them rely on volume rendering to generate view synthesis results, making it difficult to support real-time editing preview. On the contrary, 3D Gaussian splatting represents the scene as a set of 3D Gaussians with color attributes, supporting real-time rendering by surface splatting. Many 3D Gaussian-based editing methods follow this definition and has achieved promising performance. However, this representation couples the appearance and geometry of the scene within the unordered and irregular 3D Gaussians, which hinders the flexibility of appearance editing. Inspired by polygonal meshes with texture mapping, we focus on how to disentangle the geometry and texture for 3D GS-like mesh. We propose a multi-stage learning pipeline to address this issue, including geometry reconstruction, UV mapping learning, and 2D texture reconstruction. For geometry reconstruction, we follow the vanilla 3D Gaussians, splatting to obtain an initial geometry, with two additional loss terms, named opacity regularization and normal regularization, to reduce semi-transparent 3D Gaussians and align 3D Gaussians with the underlying surface of objects. To learn the UV mapping phi, we observe that if its inverse 2D to 3D function phi inverse can warp the UV space to uniformly cover the underlying surface, then the forward mapping phi would serve as a reasonable UV mapping. We freeze the parameters of 3D Gaussians and introduce two-cycle consistency loss to ensure the mutually inverse property of phi and phi inverse, with chamfer distance loss to ensure the 3D points mapped from texture space to uniformly cover the object surface. Given the UV mapping, a naive solution is to use the center of 3D Gaussian to prefetch color attributes from a learnable texture image before rendering. However, since each 3D Gaussian often covers multiple pixels in practice, this solution would map all pixels covered by a single Gaussian to the same UV location, resulting in degenerated textures and further hindering appearance editing. The main contribution of our work is to treat each 3D Gaussians as a shading surface, instead of a shading point during rendering. In most practical cases, the Gaussian should be flat and aligned closely with the opaque surface. Thus, we define the intersection between the flattened Gaussian and the ray along each pixel by the shortest axis orientation of 3D Gaussians. To achieve real-time rendering, we utilizing the first two terms of the Taylor expansion to approximate the UV coordinates. Additionally, we also remain per Gaussian SH coefficients of higher degree to capture view-dependent appearance. Here are the experimental results of our method on novel view synthesis. Texture GS can generate higher quality view synthesis results, while achieving real-time rendering speed 2,000 times faster than NeurF-based methods. Notably, Texture GS also enhanced the representational power for each Gaussian, enabling fewer 3D Gaussians to represent objects with rich texture. This page shows the texture editing results of our proposed Texture GS, including texture swapping and texture painting. Thanks to the efficient UV mapping during rendering, our method enables instant preview of the editing results to facilitate interactive editing applications on consumer-level devices. In short, we are the first to disentangle the geometry and texture for 3D GS, thereby enabling various real-time editing applications. We are also the first to treat each 3D Gaussian as a shading surface during rendering, giving researchers a deeper understanding of the relationships between mesh, NeurF, and 3D Gaussians. On the other side, the performance of our method relies heavily on the accuracy of UV mapping. Thus, it fails to tackle outdoor scenes or objects with complex geometry. What's more, unconstrained UV mapping cannot ensure semantic consistency of texture space across different objects, such as human faces. For future works, except for these limitations, how to combine our method with existing AIGC approaches is also one of the future improvements. Because most of generated 3D assets have simple geometry and rich texture, the disentangled representation can effectively reduce the number of 3D Gaussians for AIGC. If you're interested in this point, welcome to contact me for further discussion. Thanks for your listening.